Hey, this is Mr. C here. I'm going to do a little energy conservation problem with you guys to help you out with your horsepower lab. So this is number 5 from the back page of the horsepower lab. The question reads, legend has it that Isaac Newton discovered gravity when an apple fell from a tree and hit him on the head. If a 2 kilogram apple fell 7 meters before hitting him, we want to know two things. A, what was the change in potential energy during the fall? And B, how fast was the apple traveling when it hit Newton's head? So here's a picture of the problem. Here's old Newt. We have the apple right here, and it's falling a distance of 7 meters. So what I'm going to go ahead and do is I'm going to write my distance that it's falling is equal to the height of the drop. So I'll use the letter h, and that's 7.0 meters. And then I'll also say the mass of the apple, m, is 0.20 kilograms. Okay, so what we first want to know is the amount that it falls. I'm sorry, we want to know the potential energy of it. So what we're going to do is we're going to use our potential energy equation, PE, for the gravitational, equals mg times the change in height. So I'm going to use delta H, but you guys just know it as H in class. So our PE, potential energy, equals 0.20 kilograms times gravity, 9.81 meters per second squared, times the change in height, and so it falls 7.0 meters. So we get our PE equals 13.7 joules. Okay, now we want to know how fast it was going when it hits Newton in the head. So for this, we need to do an energy conservation. So the law of conservation of energy states that the initial energy, whatever you start with, equals the final energy, as long as there's no losses due to friction. So what I'm going to do is I'm going to write the entire equation before and set it equal to the entire equation after. Well, so what does the apple have before? It could have potential energy before, plus the kinetic energy before. So I'm going to write PE naught and KE naught equals, I'll do that in black. It could have a potential energy afterwards. It could have a kinetic energy afterwards. And there could be some losses to internal energy, friction, air resistance, etc. And I'll label that Q. So now we can start crossing out some things. Well, we know in the beginning of the problem the apple starts from rest. So our KE must start at 0. We also know that at the very end when it hits Newton at the head, that drops to a height of 0. So we're assuming that there's no potential energy. We're also assuming that there's no losses due to friction, air resistance, etc. So there's no internal energy. So looking at what this equation simplifies to, we see that the initial potential energy equals the final kinetic energy. What that means is the potential energy we just solved for, that 13.7 joules, equals the kinetic energy of the apple when it hits Newton in the head. Final. So I'm going to take 13.7 joules. I'm going to set it equal to the kinetic energy, and I'm going to use my kinetic energy equation, Ke equals 1/2 m v squared. And now I'm going to plug in for m, and then I'm going to solve for my velocity. So 13.7 joules equals 1/2. The mass of the apple is 0.2 kilograms times v squared. I'm going to divide by a half on both sides. I'm going to divide by 0.2 kilograms on both sides, and then I'm going to take the square root. And after doing all that, I get v equals 11.7 meters per second. And there we have it. A pretty simple energy conservation problem. As we get into the more complicated problems, if you look at this equation, it's all going to be the same variant of this, but we're going to have cases where the kinetic energy and the potential energy afterwards are not equal to 0, and where we'll eventually start having some internal energy also. So that's as complicated as it's going to get, is just plugging in more numbers into this total equation. All right, well, I hope this helps you guys out. Good luck with the rest of the lab.